Okay, so welcome to the last session of the program. Thank you all for coming. It's been a long program. So we have two talks to conclude the program. First one is Nirmalya, who's going to tell us about HKLL in de Sitter space. Over to you now.
Thank you, Suvrat, and thanks to the organizers for this opportunity. So I'm going to talk about HKLL in de Sitter. This talk is based on this paper with my student, Arundhati. And for those who know the words HKLL and de Sitter, it's basically what it says on the tin. It's HKLL in de Sitter. But let me start with the summary so that all of you can quickly catch up with what this is. So the motivation for doing this HKLL in ADS, so the idea is to construct this bulk boundary dictionaries. So we want to complete the bulk boundary dictionary given by ADS CFT, and we want to translate the bulk physics to boundary. So we can ask questions about bulk physics from the boundary, and to do that, we would like to translate this fields in the bulk to operators in the boundary, and that's what HKLL construction gives us. We start with, we construct there's some bulk field phi, and we construct an operator which is on the boundary, which is a boundary representation of the bulk field. And those kinds of operators usually have this form, where there's some conformal primary on the boundary, and we smear over it with some smearing function, and that gives us a boundary operator which represents a bulk field, meaning that it has the same correlation functions on the boundary as the bulk field, as we will discuss. And the problem that we want to tackle now is to do the same thing for de Sitter. So we don't know if there's a safe de Sitter holography exists. However, we assume that there is such a thing, and we construct such operators, or we construct such putative boundary representations for bulk fields. And there has been earlier work on this, but it has been limited to the principal series scalars, or these massive scalars on de Sitter. And the new result that we have, such as it is that for certain ranges of mass, spin, and dimension, the smearing function is not analytic in de Sitter, rather it becomes a distribution. Okay. So the talk is separated into these three sections. First, I'm going to review the boundary representations in ADS, the HKLL construction ADS, then talk a little bit about DSCFT, and finally this. So the first two sections are pedagogical, so you can, if you know this, you can safely fall asleep. I will wake you up when I get to this part. Okay, so how do we do this? So there is the ADS safety correspondence, which you all know, and this tells us, suppose I have ADS bulk, which is given by some coordinates, some Poincare patch z and x, and this tells us that if I take a correlation function in the bulk, and if I take this boundary limit, I take it to the boundary, while also scaling it appropriately like this, then I will end up with something that's a correlation function of the boundary CFT. And this is a result from ADS CFT. This is the extrapolate dictionary of ADS CFT. But what we want to do, if we want to translate all of bulk physics to the boundary, we want to get more than that. So this is telling us what is happening when I take some bulk field and I take it to the boundary. But what we want to know is, using the boundary correlators, we want to figure out bulk physics. So we want to figure out also what is going on deep in the bulk, not just at the z is equal to 0 boundary limit. So we want to construct operators, which I'm calling here phi CFT, which are CFT operators, which will have the same correlation functions in the CFT. So this is the CFT vacuum. I'm constructing this CFT operator as the bulk field has in the bulk. So that is the game I want to play. Please stop me and ask me questions at any time. Yes, coming to this, I have about 20 minutes of material, so please feel free to ask as many questions as you want. Yes. Yes, I'm coming to this. So you're going to ask, why is there a Z label on something that I'm calling a CFT operator? This is a label. This is not the Z coordinate. And this comes, as I will show you in the next slide, but also as I showed you here, this guy looks like this. So these are the boundary operators, and this is smeared, and this ZX carries this bulk coordinate labels. So this smearing operator, while weighing over this, these coefficients are weighed by these labels that correspond to the bulk point I want to see. Okay. Any other questions? Okay, so we want to construct CFT operators with bulk labels which mimic the bulk fields. How do we go about doing this? And that is what is given by the HKLL construction. So the basic idea is, so we have this phi CFT that we want to construct, and we impose this condition on it that it satisfies the bulk. So we want to construct a free scalar, for example, and we impose that it satisfies the Klein-Gordon equation, meaning that the phi CFT boundary representation has the same kind of dependence on the bulk coordinates as the bulk field has. So this satisfies this, and we had this relation. So if you look at it, this within the correlation functions, this looks like this. This is true within correlation functions. So we impose this as a kind of boundary condition on phi. So now I have these two conditions. One is a equation of motion, another is a boundary condition, and this question of finding phi CFT reduces to a boundary value problem. So I want to solve this using this, and this is what was done by these people first, and also a number of papers by Hamilton, Cabot, Lifshitz, and Lowe, after whom this is called the HKLL construction. And so when you solve this, you get a solution of this form, where this smearing function is sitting here. And so the question becomes finding the smearing function. So this has all the data about the bulk. Okay. And there are like 7 or 8 different ways of doing this. And 2 of them, the original ones, so I will just tell you about 3 of them. So this was the original mode sum approach, which is nothing but you take this equation and you expand it into the Fourier coefficient, exactly how you would solve a differential equation like this, impose the boundary condition, and finally you get a form like this. So the smearing function has this kind of form, where F's are the normalizable mode solutions. So in ADS you get this one normalizable mode, and that is what is sitting here. And this is the CK is also something that you get from the normalizable mode. So the upshot is, if you know the normalizable mode, you can construct the smearing function. That's all you need. That is all the information that you need to construct the smearing function. Another way of approaching this is using this Green's theorem, where you write the bulk field in terms of the Green function, and then by taking appropriate limits and using the extrapolate dictionary, once again you can find out the smearing function. A third approach is by Uguri Nakayama, which is that you demand that this boundary representation of a bulk field, you ask how does it transform under boundary conformal symmetries. This is a boundary operator. So how does it transform under boundary conformal symmetries? And then you demand that it should transform under boundary conformal symmetries in the same way as the corresponding bulk field transform under bulk isometries. So by making that demand, you can more or less fix phi CFT. Okay. So, so from now on, I'm going to drop this subscript CFT, and whenever I'm talking about phi, it should be clear from the context whether I'm talking about the boundary representation or the bulk field, if you want to even make that distinction. Okay. So the picture that one gets from this is like this. It's usual that when one works it out, it turns out that this bulk field smearing function is non-zero only for points which are space-like separated from the bulk point you are looking at. So I'm trying to reconstruct phi x for some bulk point x, and this will be a boundary operator which is smeared over all the points on the boundary, which is space-like separated from x. Similarly, if this is my point, it will have a smaller interval. I'm showing this picture for ADS2. In higher dimensions, it's you don't get 2 boundaries, you just get 1 boundary, and this point will be, and the support will be space-like separated from all the points on the bulk point. Okay. So this was the review of HKLL. I will pause here for questions. Oh.
So reviewing so nicely, there's some issue where all of some who work on HKLL know about distributions versus something that always comes up, right?
Yes.
Can you just?
Yeah, sure. So that comes up when we are looking at not a globe, not doing this globally for a global ADS, but we want to restrict to some kind of a ADS Rindler patch or some kind of smaller region. And whenever we want to reconstruct, so we don't need the data on all of the boundary to do the reconstruction. We can restrict to some sub-region of the boundary, but the price to pay for that is, instead of getting a function, smearing function becomes distributional, which is fine because this does not have to be a function, because what we want to look at is some 2-point function and stuff. So it's fine as long as it is a distribution. No, this is fine. This is a smearing function. I mean, you have a theta sitting somewhere, but that's it. The rest, I mean, this is the original HKLL for global. You'll have a. No, this is. I mean, no. If you do it global, this is what you get. I mean, that was it for Rindler. So if you, that was for Rindler. If you do HKLL for global, you get an analytic smearing function, and it is space-like separated for global ADS. Right. Okay. Huh. Huh. No, that's not what I'm saying. I mean, you want to take some, sorry, I don't understand. You want to take some time band. Yeah, just a whole time band on the boundary. What kind of wedge? Okay, causal wedge of this. Okay. Yes. I can write a smearing function. Yes. That will have a theta function and will not have. Yes. I mean, okay. The time band story, I don't know, but yeah, I mean, if so, you're saying that if I start with this and then if I act with the Hamiltonians, I should be able to. Or maybe the point here is maybe this is ADS2 example. This is ADS2 example. This can be confusing. So let's say I take the other side. So in this example, yes, it will also have support on the other side. In this example, no. If I take that point A. In this example, no. Not in ADS2, okay, but in higher dimensional ADS. Yes. 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 And that other side is I mean, there's only one side. Yes. Yes. Yeah. Yes.
Sorry, you must go on, but in the cases where it's a distribution, the singularities are occurring when x goes to x prime or what? Because physically, of course, the one is a bulk point and the other is.
No, I mean, just the smearing function, for example, it blows up. Yeah, you can't write this as a function. So this integral, yeah. Yeah, so for space-like distances, the Fourier transform grows exponentially. This also happens, I should say, in black holes. So not just in ADS Rindler patch, also if you have a black hole, you automatically are guaranteed to get a distribution instead of a function. Exactly. Okay. So any other questions from HKLL? No. Okay, so de Sitter spacetime, this is the picture. It's kind of looks like ADS but rotated. So we will work in this cosmological flat slicing, where instead of Z, now I have eta is equal to 0 as my boundary, and this is my future boundary, and this is the H is the Hubble constant. Okay, so just let's consider like a scalar field in de Sitter. And if we go near this eta is equal to 0 boundary, you will see that the scalar field has this kind of fall off, where there are these two kind of fall off behaviors, and both of these modes now are normalizable, unlike in ADS. And this is your delta. And now there are three possible cases, three possible ranges of values that this delta can take. And one is this, where delta is complex, and this is when the scalars are heavy. This is the principal series. So there are these three different unitary representations of scalar fields of SOD1. So principal series is this one. The complementary series is when delta takes real values, and these are the lighter fields. And then there is this exceptional series for this particular values, which we will not worry about too much. So just showing this because some of the work done previously was only for this principal series, for this heavy scalars. Now, if you consider bulk isometries on this bulk on the de Sitter, and they will form some kind of SOD1 algebra. But if you take this limit to the eta is equal to 0 boundary, you find that those isometries act at eta is equal to 0 like a conformal symmetries of a plane. And so you get this conformal symmetries. And then if you look at how this phi transforms under the bulk isometries and take the eta is equal to 0 limit, you find that O delta, OD minus delta transform as conformal primaries of dimension delta and D minus delta. And this leads one to kind of, there has been for a long time a conjecture of DS-CFT duality. The idea being that there is a CFT living maybe at this future boundary, and which corresponds to the de Sitter space here. So we don't know if this is true or not. We will assume that this is true, and then we will do reconstruction for the phi field. We are going to assume there are two independent fields. Yeah. No, but we need it for for the bulk reconstruction. I'll come to this. So I'll tell you why we need it. We need it because when we do this, let me go here. When we get the smearing functions, if we keep one, it violates causality. So these are the smearing functions like this. So put it on the future boundary, and one if you take, you don't get micro causality. So only when you do take two. So let me come to this point. Okay. Okay. So yeah. Yes. 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 So we get, so when you do this, you get this advanced green function type situation, which is not causal. And if you just have that, and if you check the micro causality, you will find that it is violated. I don't know.
You just need the state, and you need the coherent state.
But you also need the derivative of the state, so maybe also need the time derivative.
Okay.
Once you have the state, I can get the momentum. The momentum is just the functional derivative. So if I give you the full wave function of O delta, then that should be enough.
That's enough.
That's enough. But I think in a wave function language, so he wants psi and he wants.
But you do reconstruction independent of which state you are in this system. How can you do that? For example, you could have the Hartle-Hawking state.
Yeah, yeah.
You could have some other state.
No, we will need some state. Yeah.
And then I think one piece of it.
Yeah. Let's see.
Okay,
Let's discuss this. Yeah. Yeah. No. Yeah. So now, yeah. So this is the point that Sandip was making, that we now in DS we have these two boundary operators dual to a bulk field, whereas in ADS there's just one. And so we will see that in fact why we need two, or if we don't need them. So these are the differences, and a lot of things from ADS CFT you can get by translating from DS to ADS under weak rotation, but one has to be careful that not everything goes through. So, not everything, this is not correct. Okay. So again, let me pause here for any questions from de Sitter. Okay, so let me go through. So this is the problem that we want to solve. Now I have some bulk scalar in de Sitter, and this has these two kinds of fall-offs. So I'm calling this part with the eta to the power delta fall-off as phi delta, and the other one is d minus delta. So I have these two fall-offs, and we want to find boundary representation for both. So I want to find a smearing function k delta and k d minus delta. So I'm solving separately these two equations with this kind of fall-offs and getting these two smearing functions. And this was originally done by Xiao in 2014 first, and this was the results obtained by Xiao. And so you can see that, and this was done for assuming that the mass is like this. So principal series scalars, heavy scalars, it was done. And he obtained these two smearing functions. And now what happens here is that divergences appear for certain values of conformal dimension and d. So you can see here that there's this gamma functions, and whenever gamma functions have 0 or negative integers here, you can get divergence in both these denominators. So I will tell you where that kind of thing happens. Okay, so let me again show the result. There's also a theta function which is giving you the exact opposite of what we had in ADS, which is these are time-like, restricted time-like. So this is the picture. Now the support of smearing functions is only on the points of the future boundary, which are time-like separated from the bulk point we want to reconstruct.
Saying you need to express the field in terms of multiplication operator with some bulk to boundary analog.
Right.
And the
Yes.
construction operator.
Yes. 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 Yeah.
All data can be anyway. Okay.
Yeah. So now it turns out that k delta, k d minus delta can be obtained by via weak rotation from ADS smearing functions of two different deltas. Okay, if we are looking at just one ADS smearing function, I will get 1. But if I consider two different scalars on ADS, one has a corresponding conformal dimension delta and the other d minus delta, the point is that this form of the smearing function is exactly the same that you will get from weak rotation from such scales. No, that's not what was done. This was derived by Green function, and then the observation is like this form is exactly the same, that if you just exchange time and space from ADS, you will get the same form. Yes. Yes. Right. Yes. 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 Yes.
Another way, the creation and destruction operator components for a real field are complex conjugates of each other.
Yes.
So you can construct it in terms of one field and its complex conjugate.
Right. Right. Yeah.
Maybe that's what you're saying. The d minus delta
Okay.
will be related through complex conjugate.
Okay, I see what you're saying. So that's not so in the original papers that I'm discussing now, that's not what was done. So what we did was not that. What we did was doing this separately, and I will tell you more about this. Okay, so now it turns out that these two guys are both acausal. They're not causal. So if you take one of them, if you just took k delta O delta and tried to find the commutator, for example, you will find that that would violate the microcausality outside the light cone. However, when you have both these terms, then it turns out that this total phi that you get then is causal. That's when you get microcausality restored. And you also get the right Whiteman function depending on your choice of this coefficients. Yes, yes. So you are doing this reconstruction of phi, which has one this part and one this part, and then you take
You need both components.
You need both components for that.
I'm just saying they're not independent.
Okay. 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 So some other ways of doing this shown here. This came very recently from the symmetries approach that we discussed. Okay. And so one of the cases where we have divergences is to suppose you take something that is maybe a Maxwell field or some other spin, integer spin field, massless integer spin field, and then it is known that you can fix the gauge in such a way that you can rewrite this set of equations for this as a set of Klein-Gordon equations, where each of them has a mass like this and a delta like this. So this is spin, this dimension, and this. So now if you take this delta, so now if you want to reconstruct some gauge field, some spin as gauge field, you can rewrite them as this scalar fields, a set of scalar fields with this kind of delta, and then if you plug it back here, you will find that now you might get some kind of divergences. So that was an issue. because these are all integers. Okay, so what we did was that we simply solved for this two fields separately, phi delta and phi d minus delta separately, mode expanded because they correspond to some particular follow-up behavior. So the one that with the follow-up behavior, we want to identify those modes with this follow-up behavior, and want to identify the d minus delta modes with their behavior, and we want to find the smearing function corresponding to both. And so then the particular modes turn out to be some kind of Bessel functions. So this is for delta, there is something different for d minus delta, it's different for non-integers and integers. So you plug all that back and you get a formula for smearing function. And the formula looks something like this. You have a product of Bessel functions and you have some a to the power, some polynomial thing here. And the reason I'm showing this form is because this kind of integrals is well known. They are called Weber-Schaffelin type integrals. And this is exactly the same form. Well, now this, yeah. You get Hankel functions if you were to like put Bunch-Davies conditions. But what we are doing is different. What we are doing is we are identifying so the Bunch-Davies vacuum is a sum over this guys, right? J, d, delta minus d, and this. There's a particular linear combination of this. But these two have different fall-offs. So we are identifying the guy with the delta fall-off, and we are finding this corresponding smearing function. So we are separating it out. Okay. So what we are doing is not that. What we are doing is we are keeping this linear combination unfixed, finding the smearing functions for delta and d minus delta separately, and then later imposing the boundary condition, imposing the C1, C2, fixing them by demanding like a Bunch-Davies or alpha vacuum. Between delta and this phi delta and d minus delta, you're saying? Yeah, okay. 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 So then we know this is known, and this has analytic expressions only for real lambda greater than -1, and for real lambda less than -1. So in this case, for example, lambda was this guy delta minus d, and then you get distributional answers for these other ranges, and depending on the other parameters, there are some conditions on these parameters which are in the paper, and this is, or you might get some asymptotic series. The good thing here is that although distributional, there are expressions for this available which have to be interpreted as distributions in some of these papers. So I'm not showing you this, but this is the final result. So now we can plug this back, and what we get, this is for the non-integer case, what we get when our solutions are analytic, then the smearing functions match those obtained by Xiao. So exactly the same things you get from this integral also that was obtained by Xiao. However, for certain ranges of mass and dimension, the smearing function is distributional, as I just said. And this you have to check for the different things. The ranges are given in the paper. For complementary series, principal series, you will get slightly different ranges. Now it's slightly different for integer delta, because the solution is different for integer delta. You get a different smearing function here, which has the same functional form as this guy had. However, the gamma function coefficients are different. And the good thing here is that the gamma function coefficients are such that now if you have this higher spin fields here, you have those integers here, you no longer get divergences. So somehow those divergences are not appearing here. The bad thing is that because of the sign function, which depends on a dimension and pi by 2, for even dimensional spacetimes, this whole thing vanishes. And this is also something that happens in ADS when you do in Poincaré patch using green function, you get similar problems that in odd dimensions, the smearing function vanishes. So I think this is probably a problem with the construction. However, this is good, at least that the divergences are going away. Okay, so to summarize, smearing functions have been constructed for scalar fields of all masses and massless fields with integer spin. for some values of d and delta, we get smearing functions become distributional. And previously encountered divergences for higher spin fields go away in odd dimensional ds, but smearing function itself vanishes for even dimensional ds, which is something to be understood. And of course, we have not introduced interactions and so on, so that is something that maybe we'll do in the future. Okay, so thank you for your time and attention. So that's it. Yeah, so when you do this, you get this sign here, and this when d is your odd, then this whole thing becomes 0. Yeah, in even dimension spacetimes. But this is also something that happens in ADS for a particular method. There, if you do the green function method, you find that the smearing function vanishes. So I don't know if this is maybe a problem with the.
Simple-minded way to do it would be to solve the bulk.
Yes.
In terms of creation and annihilation of the And then it's true the natural modes, say in the Bunch-Davis vacuum, A and A dagger, are not the ones which fall off with the characteristics into the minus I here. So you do some Bogolian, right? And okay, you can express the field either in terms of the original A dagger or in terms of the Bogolian.
Right.
But I mean, that's just going to give you the bulk field in terms of whatever Hankel or J in terms of boundary operators, right?
Yeah.
So that way there's no issue in even or not.
Yeah. We don't know what exactly is happening. So that part we do it in this way, that we fix the C1s later. So when you do, if you have a Hankel function, for example, Bunch-Davis like here, then you have that gives you this particular combination, and then you get this particular field, which is a particular linear combination. For alpha vector, you get a different linear combination. Yeah. So this is what this is how we have done this.
I see, but all I was saying was that it should be possible to do even for even
Yeah, maybe,
Bulk solutions can be found for any.
Yeah.
Some convolution that's going.
Do this, of course, in global also, right?
Yeah, we should be
in the global. And the bulk solutions, in fact, that's the simplest way to do HKLL.
Yeah.
You just solve the bulk equations of motion and then just try and match. However, there's something that's confusing me. It should be clear, but which is in this case, we do expect to need both the field and its time derivative to reconstruct. Let's say I give you a bulk solution. I told you it's a solution of Klein-Gordon. I need certainly the initial value of the field and also its time derivative. It's a little different in ADS, right? Because I kind of gave you the field for an entire amount of time. Classical I have a field satisfies the Klein-Gordon equation, massive. And maybe this is the point that why we need D. And we need phi and phi dot on an initial slice?
You either need phi and phi dot, or you need phi and some boundary condition at the Poincare.
At the past horizon.
And that is supplied by the boundary. Yeah, you need two pieces of data, right? So usually you would say, given phi, I know, say, the state or the wave function, whatever, because I know it's.
So that's not different from here, I think.
That is just fixing positive and negative frequency for you, right? It's just telling you what is positive frequency, what's negative frequency. The positive frequency modes are the ones which in Euclidean space, continue correctly in the south pole, and negative frequency in north pole. So that can't be producing this data, right? That I give you if you're just in classical de Sitter, if I sit on the neck, for instance, and I tell you phi, you have to tell me phi dot to tell me how to evolve. So even here, I think in Nirmalya's case, if you just sit in the future and I tell you phi, you tell me also phi dot, no?
Yeah. But suppose I told you phi there and I told you something about what happened.
But we don't say that. We say, actually, in the past, we say that you have only one kind of frequency. It's not like we say that the field is 0 on the Poincare horizon. Yeah. Yeah.
And then we say something.
Yeah, so doesn't that only fix notions of what is positive and what's negative frequency? In physically, maybe global is the clearest, right? If I tell you phi, I should have solutions for all phi and I should be allowed to specify phi, and maybe you're saying phi dot is fixed, you're saying by. In the wave function, this phi dot is delta by delta phi, right? It's pi. So you give me the wave function. I write it only as a function of phi, but then I can also differentiate. And don't I need? Maybe you're saying they're related by some. Maybe they're related in the classical order because you expect it's Gaussian or something like that. So maybe you know that they're related. Yeah.
Like for the harmonic oscillator, suppose I was to ask, then of course we need to know that it's in the ground state or something to obtain the wave. Yeah. So some additional information. Then you obtain a unique function. It's the analog.
Then I guess you know it's delta by delta. Yeah, the other question.
Sorry?
Can you analytically continue to global DS?
Can you? We have not tried that. I think we, so earlier work by Xiao was also done in, I mean, they started from global ADS and analytically continued to this flat slicing. So I think, yeah, so because our results match in the where they are analytic, so yeah, it should be doable. But we would also like to do it independently in global, that we have not done.